Okay, so we are supposed to find the impedance at 1,000 hertz. So you'll notice that the frequency is given as hertz. So that's not the angular frequency. So that's F. So F is 1,000 hertz. And so that means omega is 2 pi times 1,000 radians per second. Which is something. We'll get to that in a second. Okay, and then I need to transform everything to the phasor domain. So let's see. So I'm going to do a few of these in gory detail, doing all of the stuff that I feel like I shouldn't be required to do anymore because I've done it and I now have calculators that do it. But I'm going to show you how to do it, and then I will show you also how to do it on the calculator. You do need to know how to do it, but hopefully you won't have to do all of the complex arithmetic by hand. 6,283.18. And y'all are going to really need to watch me closely on this because there's so many numbers here and I can't numbers and I don't get along. Okay, so we need to change the capacitor and the inductor to the phasor domain. So the impedance of the capacitor is minus J over omega C. So that's minus J over omega is, I'm just going to write it as 2 pi times 1,000 times C is times 10 times 10 to the negative 6, and this would be in ohms. So on my calculator, this is going to be 2 pi times, and to save myself a little bit of work, that's 10 to the third times 10 to the first times 10 to the negative 6. So 3 plus 1 is 4, plus minus 6 is negative 2. So 1 over 2 pi times 10 to the negative 2 times minus j ohms. So I'll get that on my calculator. 1 over 2 pi times 10 to the negative 2. And I get that this is negative J 15.92 ohms. Now I'll get Z of the inductor, and that is J omega L. And so that's J times 2 pi times 1,000 times 10 times 10 to the negative 3, or that's J times 2 pi times 10 times 10, because 1,000's 10 to the third, 10 to the third times 10 to the negative third cancels each other out. So this is 2 pi, which is 6.283 times 10, so that'll be 62.83. So this is J 62.83 ohms. Now the impedance of the resistor is just 50 ohms, because resistors are real, and so they're just real. Okay, so now I can redraw this in the phasor domain, and so on your quiz you'll definitely want to do this, unless he gives it to you already converted. Does he do that? Let's see. No, you're going to have to convert it. So when you convert them, you're definitely going to want to redraw it in the phasor domain the way that I'm doing right now. Okay, so it's going to look the same. Only I've got my new values here, minus J 15.92 for the capacitor, 50, and these are all in ohms, 50 ohms for the resistor, and J 62.83 for the inductor. Now, the resistor and the inductor are in series, and so I can add them. So remember I said the advantage of the phasor domain is everything works like resistors. So things that are in series, I can add them. So I will do that. So minus J 15.92. And then this will become 50 plus J 62.83. So the real parts add together and the imaginary parts add together. Okay, so this next part, they are in parallel, and so like I said, I'm going to do like maybe 2 of these out in detail. Did he say anything about how to use a calculator? Like if you had to like show how much of your work you had to show?
Show your calculation. That's all he said.
Okay. All right. So at least for this quiz, like show all your calculations and check it on your calculator. So our equivalent impedance is, they're in parallel, so it's product over sum. So it's minus J 15.92 times 50 plus J 62.83 over the sum minus J 15.92 plus 50 plus J 62.83. Now I'm going to work this as if you had the calculator that I hope you never have to use again, that you had to use in your calculus class that like doesn't do anything that y'all know the one I'm talking about. So I'm going to work it like that, although hopefully whatever calculator you have does at the minimum of some complex number stuff. So I'm going to distribute this 15.92. So let's see, so that would get 15.92 times 50 is 796, and then 15.92 times 62.83 is 1,000.25. I'll just say 1,000. So when I distribute this, it becomes negative J 796, and then minus J times J is minus J squared times 1,000. And then in the denominator, you would add together the imaginary parts. So you would add together negative 15.92 and positive 62.83. And I believe that gets 46.91. So this becomes 50 plus J 46.91. Now J squared is negative 1. So minus J squared is minus negative 1 is positive 1. So this is minus J 796 plus 1,000 over 50 plus J 46.91. Now this doesn't do us any good because we can't see what the real part and what the imaginary part is, because it's as a fraction. So I need to multiply this by the conjugate of the denominator. So I'm going to multiply by 50 minus J 46.91 over 50 minus j times 46.91. And when I do that, okay, so 796 times 50 is, get both these windows open at the same time. So foiling this out, so negative j 796 times 50 is minus j 39800. Negative j times negative j is positive j squared, which is negative 1. So negative j 796 times negative j 46.91. So 796 times 46.91 is negative 37340. 1,000 times 50, oh, I like something like that. That's 50,000. And then 1,000 times minus j 46.91 is minus 46910j over. And then the whole point of multiplying by the conjugate is that it changes it to a real number. It becomes 50 squared, which is 2500, plus, because j times minus j is minus j squared is negative 1, minus negative 1 is positive 1, so it's 50 squared plus 46.91 squared. I'm only going to do one of these out all the way because I can't handle this. Plus 2200, and then I'll combine on the top my real parts. So 50,000 minus 37340 is 12660 is my real part, and then 39800 plus 4946910. So that's minus j86710 over 4700. So then this is okay. To get my real part and my imaginary part, 86,710 over 4,700. So 1260 divided by 4,700 is about 2.7 minus j, and then 86,710 divided by 4,700 is 18.5 ohms. Whew. Okay, that was miserable. Okay, so what's that?
That's a 2.7.
That's a 2.7, yes. Okay, so what that is our impedance. So that is our equivalent impedance, and I think that was what we were supposed to get. Yeah, that's all we were supposed to get on this one. And so this is our answer, right there. Okay, we're going to do another one, but on this one, we're not going to do all of the arithmetic. We still have to do a lot of math, still have to do a lot of numbers, but not quite as many numbers because we'll let the calculator do some of it for us. What all calculators do people have in here? So get it out, make sure.
I left my TI in for it.
Yeah.
But you have one.
Yeah, I have just like that one.
I feel so bad. I want to go to my office and like get y'all. I have like I'm a calculator. Like I'm a real calculator nerd. It's like I have like one of every kind, and it's like, okay, you can't. You can't. Okay, this one, that one right there, it's just a little over $20. And can you hold it up? Yeah. And it's the one that I'm gonna be demonstrating. It's the TI 36X Pro. And it does everything you'll need. And it really does almost everything you'll need for the rest of your classes. And it is allowed on the FE exam that you'll have to take to become an engineer. And so this is the one you're going to want to learn how to use. I'm going to demonstrate later in this semester the TI-89 that has installed on it a program called EE Pro that will take a lot of these tedious calculations out of your hand. I'm just going to show y'all how that one works later this semester. But for right now, I find for calculations with complex numbers, the TI-36X Pro is far superior to the 84. If you already have an 84, it's great for some things, but it's really worth the $20 investment to get this little calculator.
What's it called again? A TI?
It's a TI 36X Pro. I'm going to go get one out of I'm going to stop the